All right, so hi everyone. So welcome to this fourth lecture. Thank you, Abdul, for the introduction and for the organization. So in this fourth lecture, I'm going to present a different type of numerical methods for meaningful games, this type will be based on deep learning tools. So in fact, there will be two lectures, this one and the following one tomorrow morning, where I will also discuss deep learning. The first one, so this afternoon, is more based on the probabilistic approach for meaningful games and meaningful control, and trying to solve it using deep learning tools. So before doing that, there is just a few comments I would like to make from the previous lecture. So I think it should be this one that we finished this morning, but I skipped one bullet point in my in the structure. So I will start with that, and then we go back to the slide deck of lecture 4 to do deep learning. But I think this bullet point will be a good introduction, because I will try to explain the difficulties that you face when you try to use some of the difficulties, at least, that you face when you try to use the probabilistic approach to meaningful games in order to design a numerical method. So here I will focus on, in fact, meaningful control, and I will try to explain a method based on more or less dynamic programming, but for a special class of meaningful control problem. So there is one difficulty that I mentioned at some point in when you want to do dynamic programming with meaningful control, and I will come back to this at the end of lecture 4. When you try to do dynamic programming, the value function is a function of the mean field, and it becomes complicated. So in general, we would like to have something finite dimensional. So one question is it possible to have a class of meaningful games, or here a class of meaningfully controlled problems, that depend only on a finite number of moments? So let's take just the first moment. Mu bar t is the expectation of xt, and imagine that the drift, the control, the drift and the cost depend only on the first moment. Then you could say, well, is it true that the whole solution to the meaningful game depends only on this first moment? We have seen in lecture 2 that this is the case for linear quadratic problems. But if you take a different problem, like this one, for example, imagine a drift which involves mu bar, so the mean, through some trigonometric function, for example, or some other formula. So it is true that each player interacts with the distribution only through the first moment. So in principle, you need only the first moment. However, it's not clear that this first moment solves an ODE, and that you can solve it by itself. Maybe it's going to solve an ODE, but maybe this ODE involves higher order moments, or involve complicated quantities of the distribution. Right? So it's not clear that you will get a closed system, forward, backward ODEs in finite dimension. Maybe you will have infinitely many ODEs coupled together, for example. However, there is
Mathieu,
a class.
sorry, Mathieu.
Yes.
Someone is asking a question.
Yes. Thank you for asking. So yes.
Yes, there are several questions. Yes, absolutely.
All right. Thank you. So there are two questions at least. One is related, okay, what we did in the morning. Yes, I could have started with that. So how about I finish this, and then maybe I will leave some time for question about this whole slide deck, if you don't mind. And the next question is in part 4. Yes, MKV FBSD system. So I say that the link between MFG and the yes. Okay, do you want to?
Sorry, Mathieu. It is the same question.
Yes.
Safwan has asked if he could ask, and the second part is the question. Sorry.
I see. Thank you for posting the question. So, okay, so let me read the question. Is there any reference that gives condition on the MFG problem in order to have existence such that so the optimal control hat alpha makes capital B and capital F Lipschitz? Okay, so let me answer right now since I read the question. So it's related to the FBSD system, which should be somewhere here. And so we have this capital B, capital F, which implicitly correspond to B evaluated at alpha, and also the running cost evaluated at alpha hat. So one question is, what do we need on B? You see that here, B is basically the composition. So capital B is a composition of little b and alpha hat. So so you need some condition to have alpha hat Lipschitz, for example, and then B Lipschitz as well. So yes, it's possible to have conditions on the model, meaning on B, F, and G, so that the optimal control will have enough regularity. For example, you can use arguments from PDE theory. So if you're interested, I can send some references. I'm pretty sure that if you check the lecture notes of Pierre Cardaliaguet, for example, which was on one of the first slides, and you can find some argument, at least for some class of mean-field game. And if you check the book of François Delarue and René Carmona, you will find also a lot of results about regularity. So I hope this clarifies the question for this part, but it's a good question indeed. I don't discuss too much regularity. I apologize. It's more hand-wavy, the presentation here, because I try to convey the main ideas, but it's a very good question. In practice, when you want to analyze the system or when you want to analyze a numerical method, convergence of numerical methods, indeed regularity is important. All right, so let me resume here. So what I just said is that it's not because the drift and the cost depend only on the first moment that you will be able to solve the mean-field game as we did in the linear quadratic case. However, there are some cases. So there is a class, you can make some assumptions on the drift, on the cost, such that the mean-field control problem can be rewritten as an optimal control problem for a number of moments, but a finite number of moments, for example, up to p, let's say. So you see that here there is no distribution anymore. You only have what I denote by x underline, where x underline is a collection of moments up to order p. So, all right, I see there is another question. So maybe I will follow up on this after finishing this part on the mean-field control. So here we have a finite number of moments. So in some sense, it is finite dimensional. It is back to an optimal control problem in finite dimension because the state is this collection of moments. It's not completely clear that the collection of moments has a dynamics which depends only on the same moments, but here what is claimed is that indeed the evolution of x underline depends only on x underline and not on moment of higher order. So this is not trivial. You need some structure on B in order to have that. It's not automatic, but in some cases it's true. And in these cases, we are back to a finite dimensional optimal control problem instead of an optimal control problem in the space of distributions. So we can apply somehow standard technique from stochastic optimal control. And one of them is to use the dynamic programming principle with backward iterations. But when you do that, there is a difficulty, which is that you need to estimate a conditional expectation. So in order to go backward in time, you need to estimate the value at the next time step, which is given by your value function, but there is a distribution over the states. And so you need to compute this expectation given your current state. And it's not so simple because you are controlling the transitions. So you control the transition and this influences the state where you will end up. And so this conditional expectation is not so easy to estimate. So there are several techniques to do that. One of them is to use regression method. And the idea is basically this conditional expectation, you want to see it as a function of the current state, and you decompose it on a set of basis functions. So the conditional expectation is a function of x, t, and alpha. And we want to find this function. And the way we find it is by decomposing it on basis functions that are predefined. So we need to choose these basis functions. And once we choose them, we have to find the coefficient here, for example, by using a regression. So one of the ideas that has been developed using deep learning is to change that and to say, well, instead of using this formula, we are just going to plug a neural network parameterized by theta and taking x as an input. So instead of decomposing the function on a set of predefined basis functions, you use a parametric form with parameters. So it can be a neural network or it could be something else. And then same thing, you try to tune theta in order to minimize this, this L2 loss. So I will come back to this a bit later when we discuss neural networks, but I think that's maybe one thing where it's a very simple idea. So you see this method, backward dynamic programming, conditional expectation estimated by projection on a set of basis functions, because conditional expectation is an L2 projection. And instead of using basis functions, which are usually hard to choose, if you don't know the solution, it's hard to choose the basis functions. If you take too many of them, it would be very expensive to do the projection. If you take too few of them, the projection will be of very bad quality. So in high dimension, it's pretty complicated, but you can replace that by a neural network, which is a parameterized function of your current state. So this has been developed in particular by Yuan Pham and co-authors through the name of a deep backward dynamic programming method and several variants that I will mention later. So that's about what I wanted to say on this method. There are a few more slides, but I think this is a nice transition to deep learning. I can briefly go through this. So another method is quantization. So in particular, Gilles Pages has worked a lot on this, and on his website, or the website given at the bottom, you can find grids of points and the associated weights in order to do quantization. And the idea is to discretize space and to discretize the jumps for the noise. And then based on that, you can also estimate conditional expectations. It works in dimension larger than 1 to 3, but in high dimension, let's say 15, 20, 100, then it becomes costly. So it works in higher dimensions than PDEs, I would say, but still with neural networks, we will be able to go in even much higher dimension. So yes, that's about it. And this was the conclusion. So I think there was one question, and let me know if you have more questions on this slide deck. Feel free to post them in the chat. So I said that we have a contraction for small t. Did I mean small t and Lipschitz BFG, or just small t and any BFG? I meant small t and Lipschitz coefficients, but not necessarily with I think there is a trade-off between having a small time horizon and having small Lipschitz constant. And in some cases, you can balance the two. So you can take a very small time horizon, and maybe you have a little bit of wiggle room on the Lipschitz constants. Sometimes you need both of them to be small. So for this, you need to do the computation in your model. And I can point you to papers where the computations are done explicitly if you want. How to choose the base and M. So I imagine you refer to the set of basis functions. Here, yes. So there is a set of basis functions here, and there is capital M, which is the number of basis functions. And that's a very good question. I don't know if there is a good general answer. I think it's very problem dependent. So the idea is you want your L2 projection to be good, to be accurate, but of course it depends on the function you are trying to approximate. So if you know something about the function you try to approximate, for example, you know that your function is close to a polynomial of degree 2, maybe you are going to use polynomials. But if you have some other information on your function, maybe you choose differently your set of basis functions. But indeed, it is one big trouble when you try to implement this method to choose in a suitable way the basis functions. And somehow the neural network approach kind of circumvents this problem because you put a neural network. But of course, you have to choose the architecture of the neural network. But I would say in general, you over-parameterize and it seems to work well. Whereas for basis functions, if you don't choose them very well, it's not very accurate. What about Machiavellian calculus? Yes, I think it's a good question. I'm pretty sure some people have used that, but I don't know. I don't know exactly. But I think that could be used. I don't know if it would be more efficient, but yeah, it's a good idea as well. So yeah, if you have some references, I'm happy to discuss afterwards. So here I present just two methods, but I'm sure there are other methods to present conditional expectations. But in general, in high dimension, it's, as far as I know, it's still a difficult problem. Okay, so if there are no further questions, or you can ask more later if you want, I would like to start this part on deep learning. So I will introduce a bit neural networks and then present some algorithms. In fact, I will present mainly two algorithms. The first one is really for mean field control, and the idea will be to just parameterize the control as a neural network and try to learn this control by minimizing the cost. So we are not going to use optimality conditions. We are just going to aim for the control directly. And this is suitable for mean field control, but not really for mean field game, which is a fixed point problem, or at least it's not so straightforward. The second class of algorithm will be for Makin-Vlasov FBSDEs. And this one you can use for I would say a generic Makin-Vlasov FBSD, whether it comes from mean field game or mean field control, whether it is obtained by using Bellman's principle or Pontryagin principle, etc. Of course, you need some assumptions in order for the method to work, but it's for FBSDEs of Makin-Vlasov type and not just for control problems. In fact, the second method will be somehow a corollary of the first one. So the main point is the first method, and the second method, with one extra trick, we reduce FBSDEs to control problems, and then we solve the control problem using deep learning. So far, we have discussed ODE systems for the linear quadratic setting, where the dependence is on the mean, but as I've just recalled, it's not because the cost depends on the mean that the whole solution will be computable by ODEs, right? So if it depends on the mean in a complicated way, you may still end up with a system of PDEs and you need to solve it. So linear quadratic is really very specific. Then we discussed forward-backward PDE systems. So this was this morning, and forward-backward SDE system this morning and this afternoon a little bit. In fact, the methods I've presented are not exhaustive. So here are some references, but even this list is not exhaustive, just to give an idea of the diversity of methods. So what did we cover, just to summarize? So we did finite difference and Newton method, semi-Lagrangian, augmented Lagrangian, primal dual, and then I didn't discuss the other ones, but you can check these references if you are interested. Numerical methods based on the probabilistic approach. So this morning we discussed, in fact, these two methods, but there are other ones. So In fact, there are some advantages to these methods. In particular, they tend to be very efficient and they can be analyzed in detail. So I haven't insisted too much on the numerical analysis aspects, but for example, finite differences have been studied a lot, and we have a big toolbox to analyze finite difference systems, convergence, etc. And same thing for the other methods I've presented before, even the Monte Carlo method. We have a pretty big toolbox to study these methods and to prove convergence results.
Mathieu, so, there is a question.
Yes. Sorry, thank you. What about, yes, B-splines or wavelets? Yes, I think it's a good idea. I'm not aware of references doing that, I think, but yes, that's a good idea. So there are other approximation methods that can be used indeed. And maybe this is a little bit, so maybe what you suggest could be combined with what I'm going to present now using neural networks, but maybe you could replace neural networks by wavelets or some other classes of parameterized functions. So indeed, now the goal is to try to go in higher dimension and maybe with more complicated structure. So maybe you have noticed that very often in the PDE papers and in the references I gave earlier, you assume that B is equal to A and f of x and a, f of x a m is equal to some function like this, but usually we replace it by 1/2 of a squared, and then f0 of x and m. So we don't have to take a square. I think many results are more general than that, but it's quite common to assume a separate dependence in A and in M, although the method works even beyond that. I've shown the case of congestion, and it's quite common to assume that the drift is just the control. Again, I'm sure these assumptions are made very often for the sake of convenience, but still, in terms of structure, I think we need some quite restrictive assumptions for many methods. And the hope, I'm not saying that we are there yet, or we cannot prove it yet, maybe, but the hope is that with machine learning, we would be able to tackle very complex problems because machine learning has been successful, at least empirically, in many very complex and very high dimensional problems. So I will say motivations, I will say the hope, and there is a lot of work to be done in the analysis, right? So the previous methods have been or can be analyzed in details in many settings, and I think there is a lot of work to be done to extend beyond the existing papers. And for machine learning, there is very little so far, and there is a lot to be done to prove almost anything. So in these lectures, we are going to use deep neural networks and deep learning. So in fact, there are two key ingredients. One is to have an approximation technique, I mean, a set of approximators. And for this, we are going to use deep neural networks. And the second ingredient is to train or to tune the parameters of the neural networks. And we are going to do that using stochastic gradient descent or some of its variants or variations. If you want references, here I give just two of them, but there are many books on deep learning. Here I'm not going to need a lot of background on deep learning, but I would like to introduce these two key ingredients that I just mentioned. So don't worry if you don't know deep learning. I will present what I need for the rest of the lecture. On the other hand, if you want to know much more, then feel free to reach out and I can provide more references. So let's take an example of regression. So what is regression? You have an input X and you have an image f of X. And basically, you want to find this function f, but you don't know it. So what you do is you define a loss function, which is basically a function of your candidate t and a sample c, and then you evaluate the, for example, L2 distance, Euclidean distance, between phi of x, which is the candidate output, and f of x, which is the true output, right? Remember that xi is the input and the label. So if you want to think of this as a label or as an output, a correct output. But more generally, you can be interested in a general form of this problem where you define a loss function of phi. Phi itself is a function. And you want to minimize L of phi and xi in expectation over xi. So you don't know the inputs. There are many possible inputs, xi. And the problem is that you don't know the distribution. So the first thing is we cannot minimize over all functions phi, even if you impose some regularity, or maybe you take linear functions, then it becomes a linear regression problem, for instance. But if you want to allow for more general functions, you can take a class of parametrized functions, parameterized by theta. So linear function is one example with 2 parameters, but you can take more general classes of parameterized functions. And here, the example I want to give is feed-forward, fully connected neural networks, although there are many more architectures. But what we mean by a feed-forward, fully connected network is a function where you take your input, x, you multiply it by a matrix. So x could be multidimensional. You multiply it by a matrix, W1, you add a vector. So here, beta 1. And this operation gives you a new vector, and you apply an activation function, coordinate-wise. So this function could be, for example, the positive part, or it could be a function which is 0 and then positive. It could be a function which is a sigmoid, like this. Some kind of nonlinear function. In practice, we need maybe some assumptions to prove theorems of approximations, but think about the positive part of the sigmoid function, and we apply it on each coordinate of the vector. Now we take this vector, and we do the same thing. We multiply by a matrix, we add a vector, and etc. We apply an activation function. So each of these operations is what we call a layer. It's basically just a composition of functions, linear and nonlinear functions. Okay, so if you didn't know what a neural network is, here is what I mean by neural network, or at least that's what you can have in mind, even though there are more complicated architectures. What we call the depth is the number of layers, so the number of compositions, and the width is the dimension of the vector inside, because beta here is a vector and W is a matrix. So what we call the width is the dimension of beta. So there are many other architectures. If you want to have fun, you can check the neural network zoo, where you see pictures of neural networks. So there is a graphical representation of a neural network that I'm skipping for here because I don't need it. But you can see many different architectures. In particular, convolutional neural networks are used in image recognition, shape recognition, etc. Recurrent neural networks, and many others. In fact, in some of the simulations I'm going to show, not today, but tomorrow, sometimes I use other architectures that feed-forward fully connected. So it's not, I present this one for the sake of simplicity, but sometimes it is really helpful to have other architecture. Successes in many fields, including in games. So you have probably heard about AlphaGo and other games where neural networks have been used. They are one of the ingredients. A combination with reinforcement learning tomorrow, universal approximation theorem. So I'm skipping this, but that's at least that was one of the very strong, maybe theoretical motivations behind neural networks. In practice, there are many things to discuss beyond the universal approximation, but what it says is that basically, if you take a continuous function on a compact interval or a compact set more generally, then there will be a neural network that is going to approximate it arbitrarily well, provided you take the neural network large enough. And this is true even for a neural network with a single layer. So basically, the way it works is just by density. If you want, you can think of this kind of results as a density. It tells you that for some classes of functions, for example, continuous function on a compact set, the set of neural networks is dense in the set of continuous function on a compact set. In a very hand-wavy style, and you can go beyond continuous functions. And of course, you need some assumptions on the activation function in order to get such approximation results. There is a growing interest on the connection between neural networks and numerical analysis. So most of the development of neural networks is done, let's say, empirically, mostly. But recently, there is more and more interaction between neural networks, deep learning, and numerical analysis. So, for example, this book by Bruno Desprez, where he really makes some connections with classical numerical analysis. So, one thing that is nice. Sorry, I see there is a message in the chat. Sorry. So, what is the loss functions U takes? So, I am not sure. I don't have any U, but maybe, okay, I will be more precise about the loss function when I solve mean-field control. So I think it will be more precise very soon. Otherwise, feel free to ask me the question again. So one thing that is nice with these neural networks is you can compute, because the function is parameterized. So you can implement the function completely, and you can also compute its derivative or derivatives. You can compute the gradient with respect to the parameters. So gradient with theta here means that I take the derivative with respect to theta, which is a parameter. And gradient with respect to x means I take the gradient with respect to the input. So remember, the neural network has in fact two inputs, but the first one is just the parameters. If I go back here on the left, you see that sometimes I will use the notation phi under phi subscript theta to mean that theta is a parameter. It's kind of fixed when you want to evaluate the function at x. But if you change theta, of course, you are changing the function. So theta is really an input of this function. All right, so you can also compute partial derivatives. So you can take that as an exercise if you want. Compute the gradient with respect to beta L, compute the gradient with respect to W2, etc., and see the formulas that you get. All right, so second ingredient, stochastic gradient descent. So I come back to the motivation. Imagine you want to minimize a loss function, which is a function of phi. But this loss function is defined through an expectation. But we don't know the distribution of xi. We don't know it exactly in general. So even after parameterization, we still have an issue. So parameterization helps us to have a loss function, which is a function of theta, and then we minimize over theta instead of minimizing over all functions, but we still face this issue. So here, what we can do is we can use samples and approximate the expectation using samples. And that's the idea behind stochastic gradient descent. So at each iteration, what you do is you pick a sample. So for regression, you would pick a pair of input and output, x and y. And then you use your candidate, you use your neural network. You see if it has the correct y on this x. And if not, then you adjust a bit the parameters. How do you adjust the parameters? By computing the gradient of the loss with respect to theta. So computing the gradient can be complicated because you have to differentiate through the loss function L, and you have to differentiate through the layers of the neural networks because the dependence on theta can be complicated. But in the past decade or 20 years, there have been a lot of libraries that have been developed to do that for you. So in practice, if you use libraries such as, TensorFlow or PyTorch or JAX and others, you can do that automatically, or rather the computer does that for you automatically. So that's what I mean by automatic differentiation, but in a smart way so that it's really done efficiently using so-called backpropagation. Or JAX works differently, but at least in TensorFlow and PyTorch. So, all right, there are many comments to make. These were my few slides about deep learning. So there is a lot more to say. For example, how to choose a learning rate. So in the stochastic gradient descent, I didn't discuss that, but there is a learning rate here which describes how fast you update your parameters. Small learning rate, you don't update a lot. Big learning rate, you update a lot. Of course, update a lot or not depends also on the size of the gradient. So if you have a small gradient, maybe you want to use a large learning rate, or vice versa. Or so it really depends on the situation. And one popular method is ADAM, which updates the learning rate automatically for you. So there is a rule inside which chooses the learning rate for each iteration, and for each parameter, you may have a different learning rate. Just to give you an idea, this paper is like 2014, and I checked yesterday. It's already cited something like 150,000 times. 150. So it means that since 2014, there is, let's say, 150,000 papers using or citing this one. So it gives you an idea of the growth of the literature. And of course, I'm not going to review this literature here. There are some proofs of convergence. So at least as far as back to Robbins and Monroe, and you can check the literature on stochastic approximation, for example, this book of Borkar. There is a lot to say about the choice of hyperparameters. So the architecture of the neural networks, the initialization of the parameters, the learning rate, the choice of the loss function. So this was one question. And I will mention this a little bit in the problems I will describe. But in general, it's a very broad topic. So there is one question about stochastic gradient or Adam method convergence. Yes, there are some proofs of convergence. So here I mentioned some of them for stochastic gradient descent, somehow the standard versions. And I think there are some cases in which you can show Adam converges. But usually this is for very simple architectures. And in practice, you use deep and complex architectures. So I don't think we have a proof of convergence for the very general case that is used in practice. There are several types of errors. So I mentioned that just so that you have it in mind, because maybe it's a different paradigm from than standard numerical analysis. So what are the types of errors we should care about, at least, even if we don't always prove rigorously bound on the type of error, but what are the kind of pitfalls that we can expect? So imagine you want to minimize a loss of a function phi. So this is what I was denoted before J phi, but here I call it population risk. So I use a notation R. And you see, I take the example of a regression where the goal is to match the label Y. So this was my notation before. C is equal to X and f of X, or you can denote it X and Y, but the function f is unknown, and you would like to learn it implicitly by looking at the images Y associated to X for many different pairs of X and Y. So that's what we want to minimize. And ideally, we would like to bound this. So this is the true error that we are going to make. You give me a candidate phi, I plug it in this R, and I see the result. If it's big, then it's bad. If it's small, then I'm happy. And if it is 0, then it is perfect, right? This is what we are aiming for. But in practice, we cannot even compute this expectation, right? Because this is the expectation over all possible samples, and we are not going to see all possible samples. In fact, so in general, Y is a little bit random. So here, I will say, if it's deterministic, then it's much simpler because you just need to see each sample once. So usually there is a bit of noise here, which makes the problem more interesting. So we make an hypothesis class, in the sense we give ourselves a class of functions among which we are going to look for a solution. So here, for example, neural network with a given architecture. So when I say a given architecture, for example, you can take the feed-forward fully connected network with a fixed depth, fixed widths, and also fixed activation functions. So once I have determined the depth, the width, and the activation function, the only thing that is not known is the value of the parameters, right? So I consider all possible values of parameters, and this gives me a class of function as functions of x. In practice, we have a finite number of samples. So we have what is called an empirical risk, and we have a finite number of optimization steps, for example, k. We are not going to run stochastic gradient descent forever. All right, so I'm going to use this notation to define 3 types of errors. Sometimes there are different names in the literature, but I think these ones are quite standard. So the first one is approximation error. So this one is basically, let's imagine you have all possible functions. You have your class of possible candidate functions. So for example, neural networks with a certain architecture. And but it's possible that the function, the true f, is outside, right? Maybe the function you are aiming for is not a neural network. So there is some kind of incompressible error. What I said before, the universal approximation says that if you consider neural networks with infinite width, then you can approximate any, let's say, continuous function. But if you restrict yourself to a given width and a given architecture, then you will have some kind of incompressible error. I think there is a question. Maybe feel free to ask the question in the chat if you want, and I will answer. Okay, so the first one is the approximation error. It's some kind of incompressible error based on your class. So this could be one reason why you see a big error in your algorithm, or why your algorithm is not precise, just because your neural network is not deep enough or wide enough, for example. And this, the algorithm cannot do anything about it. Even if you train for longer, it's not going to change anything. Estimation error. So you see that the estimation error is based on the fact that you use a finite number of samples. So here the idea is, well, you try to minimize the empirical risk. That's what you do in practice. We don't really minimize. So at the beginning, we want to find ideally the arc-mean of the true risk. But we cannot compute R because it depends on an expectation. So we replace it by the empirical risk, and we find a candidate. So this candidate is somewhere, maybe somewhere inside. It doesn't have to be the closest one. And why is that? Because we are making an extra error since we use the empirical risk instead of the true risk. So here there is an extra error, which is called the estimation error. This one, you can fix it if you use maybe more and more samples, let's say. And the last one that I want to describe is the optimization error. This one is due to the fact that, well, in practice, how do we get this arc-mean here? Well, we don't. In fact, what we do is we approximate it using, for example, stochastic gradient descent. And we use stochastic gradient descent. We are hoping that it converges towards the arc-mean. Converges meaning that it use infinitely many steps. And if you are lucky, because sometimes it is stuck in some bad local minima, or it will jump around because it's stochastic after all. So after k steps, what you get is an approximation. And this approximation induces an extra error. So phi ks is somewhere here, and you have some distance. And in the end, well, maybe you are interested in the total distance between this is the object that you really get as a result of your optimization with a finite number of steps, finite number of samples, and a class of functions versus the true f here. And this is what we call the generalization error.
Mathieu, there is a question regarding epsilon.
Thank you. So question epsilon is approximately, let's see. So, yes, okay. So here I have several epsilons, and in fact, you don't really choose them. I think these epsilons are more like theoretical quantities. I'm not saying you can really compute them, but the epsilon approx, epsilon estim, epsilon optim here, you sum them to get the generalization error. And these are quantities that are convenient to have in mind, and sometimes you can bound them. So there are results for some classes of functions, and for some problems, there are theoretical results on these types of errors. But in practice, you don't really observe them, or you don't really choose them directly somehow. There are consequences of your choice of function and of your problem.
They don't serve as any stopping criteria.
Right, exactly. Yeah, that's my point. You cannot really use them as a stopping criteria because you don't know f. Here, phi hat you never, so phi star you never really get it, and phi hat you never really get it. So the only thing that you have in your hand is this one. That's what you have when you run the algorithm, and the rest you don't know. So you would like to bound these errors. Maybe you can do it theoretically, but in practice you cannot really compute them. Okay, but nevertheless, I think it's good to have these types of errors in mind because, I mean, if the algorithm doesn't give a good result, if you feel that your algorithm is not good or is not giving a good result, it could be for any of these reasons, right? And for each reason, you have a different cause and then a different way to fix the issue. So I think that's helpful to have this in mind. All right, so two methods. The first one will be for mean-field control. So actually, I will start with standard optimal control. You see that what I've presented before is for optimization problems. There is nothing about time dependence, right? There is no time involved. So how can we recast an optimal control problem as an optimization problem? Well, basically by forgetting time. At least that's probably the most naive way to do it. It's just you forget time and you treat the problem as an optimization problem. You choose a control, you compute the loss, which is the total cost, and then you try to tune the control until it minimizes the loss function, right? And you kind of forget that the loss is computed using time. I mean, you forget in the sense your guess for the control is not really going to depend on that. So again, we cannot minimize over all possible controls. So we parameterize them, for example, using neural networks. But if you want to use wavelets or something else, why not? So these ideas go back to at least, for example, the paper I'm citing here, but probably others around that time. But around that time, it was around 2005, it was pretty hard and pretty painful to implement neural networks because you had to do everything by hand, in particular, computing the gradient of the neural network with respect to the parameters. It's painful, particularly when the neural network is deep and the architecture is complex. We didn't have Adam, we didn't have a lot of tools. So at that time, neural networks were not as efficient as today. And more recently, this type of method has regained interest. In particular, this paper of Han and E managed to solve control problems in very high dimension using this approach. So here is the idea mathematically. You take a standard control problem, so no mean field for now, and the control is alpha. Let's take Markovian controls, functions of t and xt. What do you do? First thing is you replace the control by a neural network, which is here going to be a function of t and xt. So two components. Okay, so now since the neural network is completely characterized by theta, the goal is to tune theta in order to minimize the cost, which is expressed as a function of theta. You cannot directly compute the time integral, so you discretize time, for example, using an Euler-Maruyama scheme or something more complicated if you like. and you end up with this type of problem. Now you have an expectation here. I'm not writing the Xi, but it's an expectation over some kind of random sample, right? So what is random here? Well, actually, it is precisely what is in purple below, and it is x0 and delta w, which is an increment of the Brownian motion. So if you give me x0, you give me a collection of increments of the Brownian motion, then I can compute this expectation. I mean, then I can compute one realization of this cost. If I do this many times, I can have an approximation of the expectation. So that's how you can implement stochastic gradient descent to minimize the cost for an optimal control problem. The neural network induces an approximation error because maybe your optimal control is not exactly, cannot be matched exactly by a neural network once you have chosen the architecture. And time discretization also induces extra error because you are not going to get the exact cost. So this one is not really any of the cost, any of the errors I have described before. It's more related to the fact that you have a continuous time problem and you are approximated by a discrete time problem. So you are going to have some error no matter what. So to implement SGD, one sample is going to be x0 and the collection of the delta W. How can we do that for mean field control? So it's going to be pretty similar, except we have one extra ingredient, which is the distribution. So we need to do something about the distribution. So here mu t or mt, so the law of ft. Remember that in a mean field control problem, the distribution is really the distribution controlled by alpha. So let me stress this. Here mu is with a superscript alpha everywhere to stress the fact, and same thing for x, like this, meaning that really x is controlled by alpha and mu is the law of x alpha, so it also depends on alpha. Okay, so what can we do? Well, let's follow more or less the same steps. We are going to replace the control by a neural network, discretize time, but we are also going to do some approximation for the distribution because the distribution is a probability measure, and I don't know how to put a probability measure directly in the computer. I need to do some finite dimensional approximation of this probability measure. If f and b and g depend on mu in a relatively simple way, then you could have some simplification. So in fact, the problems I'm going to treat have a specific dependence in the mean field. So the first step will be here to replace the mu by an empirical distribution. This is probably the simplest thing you can do. To represent the probability measure, you replace it by n samples, right? So this is what we see here. Now, this is still high dimensional, so it can be cumbersome, but if, for example, everything you need is an average or maybe a convolution or something like this, these are quantities you can compute easily based on n particles. However, I'm not going back to an n-player problem because here I am not considering controls that depend on all the agents. The control depends only on your own state, I mean, only on the state of xi. We replace the control by a neural network, and we discretize time as we did in the previous case. Now we have a fully discrete problem that can be really implemented and for which we can use stochastic gradient descent. So we have two sources of errors besides the neural network: finite population and time discretization. Again, here we stick to decentralized controls because that's what we expect to have in the MFC problem. In the MFC problem, we really don't need to let the control depend on the distribution because the distribution evolves in a deterministic way. For n-agent problems, in general, to be really optimal, you would need to consider controls depending on the state of everyone. But here we use decentralized control, and so it will be approximately optimal for an n-agent problem. So using this kind of scheme, what you can do is you can show some kind of approximation error, saying that compared with the original problem, so this is really the MFC, and this is the discretized problem with n particles to approximate the distribution, n t time step, and some parameters here. So theta is finite dimensional. I'm not taking neural network with infinite widths. I'm taking neural network with a finite number of neurons. So there is a dimension here, which is the number of parameters in your neural network. And what you can show is that the difference between the two losses is going to be bounded by 3 epsilons, one which depends on number of particles, the other one the dimension of theta, and the last one nt. So these epsilons go to 0 as the parameters go to infinity. And in fact, you can get rates of convergence, at least you can get upper bounds. So I'm going to show that. Okay, I'm going to show that next. The estimation error can be tackled. So the estimation error is related to the number of samples. So here, this is not quantified, right? I'm not saying anything about the number of samples. This can be quantified using techniques that we have used in a different setting with René. And the optimization error, as far as I know, remains to be studied. So this is the error done by stochastic gradient descent. And as of now, I cannot tell you after that many steps of stochastic gradient descent how close you are from the true solution. All right, there are many extensions and refinements. So this is a result we obtained with René Carmona, and you have the reference here. I would like to explain the main ingredients of the proof because I think, first of all, it will partially answer one question I got in the first lecture. And second of all, it shows a little bit that really this is at the intersection of different topics, and you can use tools from different directions and combine them. So in order to get the previous proposition, we have 3 epsilons. So let's have 3 results, one for each epsilon. Epsilon 1 tells you that the dependence on n is going to make the error smaller when n increases. So in fact, here you get a rate of convergence, which is n to the more or less n to the minus 1 over d, where d is a dimension. And so this tells you how many particles somehow you need. And you see that in principle, in high dimension, you need many particles. But this result is for a relatively general dependence on the distribution. So if you have a very specific dependence on the distribution, maybe you can converge faster. And this is based on a propagation of chaos type of argument, which is developed in detail in the book of Carmona Dorari. The second step is to quantify the approximation by a neural network. So here, we want to replace alpha by a neural network. So you have the optimal alpha star here, and you have a candidate neural network, and you would like to know how close you can be. And you cannot be perfect because your neural network has finite widths, finite depths, and so maybe alpha star is not exactly in this class of functions. So here's the approximation error that we got is of this order. It's based on a work of Mascar and Michele, which is a little bit niche, I think, because we had some technical problems related to regularity precisely. So earlier, someone asked me about the regularity of the control. And precisely here, this is the kind of results that we need. We need the optimal control to be smooth enough so that we can approximate it precisely by a neural network. You can imagine that if you have a discontinuous function jumping everywhere, it will be very hard to approximate. You will need a huge number of parameters. But if you have a function which is almost a constant, then it should be very easy to approximate it, at least in soup norm. So regularity of the optimal control is important, even to get such theoretical results of approximation by a neural network. And here, the technical issue that we had was that we needed to approximate not only the optimal control. So sorry, this should be alpha. We needed to approximate not only alpha, but also the gradient of alpha using the neural network. So you see you have a function, maybe this is your alpha star that you are aiming for, and I can design a neural network which approximates it very well, which is going to be something like this. All right, so this is a very good approximation of alpha star if I take phi hat theta like this, but in terms of gradient, it's terrible, right? The gradient is completely wrong. So if you need to approximate a function and its derivative, of course, it's more complicated than just approximating the function itself. In fact, I'm going to need this kind of remark in the lecture tomorrow when we try to solve PDEs, because when you try to solve PDEs, you really care about the derivatives. Okay, the last step is the time discretization. So this is more or less standard, let's say. Euler, Mayuriyama scheme have been studied a lot. What is not standard, though, is that here you have a system of n particles, and you want to discretize time. So if you do it directly, you are going to get constants that depend on n, because n is a dimension, or n times d. D is the dimension of one particle. So n times d is the total dimension of the system. If you use Euler's scheme naively, you are going to get constants depending on this quantity. And you don't want the constant to depend on n, because later you want n to go to infinity, or you want n to be very large. So basically, you have to reduce the proof by hand, but thanks to the symmetry in the system, you can get an approximation which is independent of n. So this epsilon 3 is independent of n, and that's one key technical point. In fact, this is reminiscent of earlier works by Bossi and Thaler, also on Makin-Vlasov equations and Euler scheme for Makin-Vlasov dynamics. So maybe just a few more slides, and then we can take a short break. So before I show some numerical illustration. So what is the idea to apply stochastic gradient descent? You can really recast the problem in the form I started with at the beginning. So I had a question about what is the loss function. Well, here you have a concrete example for this capital L. And the definition of capital L is complicated because it is the sum of the running cost plus the terminal cost. And to compute this running cost, you need to solve the dynamics, right? So L is pretty complicated, but this is a very specific example. One sample is an initial state and a collection of Brownian increments for all the particles. And then based on this point of view, you can apply stochastic gradient descent. So the structure is something like this. You start with your vector of x zeros. So this one is in dimension R, is in dimension nd, because you have n particles. From here, you can deduce the empirical distribution. You plug x0 in your neural network. And based on all these informations, you can get the running cost at time 0. So at time t0. You can also get the evolution. So using your neural network, you get the next point in time. And then you can repeat. So you repeat. You do that as many times as you need. But you see that my red box here, this is, at least in my notation here, this is the same neural network used multiple times. So you use the same neural networks for each time step, and at the end you get a total cost, and this total cost is your loss. And then you have to do one gradient step. So you see, now if I ask you the gradient with respect to one of the parameters in theta, is going to be pretty painful to compute the gradient, right? But TensorFlow or PyTorch does that for you automatically. Okay, I'm going to show some numerical illustration. The first one will be a linear quadratic example for which we know the solution exactly, but maybe, let's see. Yes, maybe we can take a short break, just a few minutes, and then I will show the numerical examples. I will show some code, and after that, we move on to the next method. So maybe, let's say, 3 minutes, 3 minutes break. So we restart at 2:40 Morocco time and 3:40 France time. And if you have some questions, you can post them in the chat. Okay, so maybe we can restart. Let me just show the slide. And so there are 2 questions in the chat. So thank you for your questions. The first one, is it necessary to have regular solutions? I would say yes to some extent. At least if you want to prove approximation results, you need some regularity because the approximation results by neural networks work with some kind of regularity. But actually, there is really a big diversity of results. For example, there are some results approximating functions in Stoboloff spaces using neural networks, or just functions in various spaces. So if you have a specific example, maybe it works. You need some regularity, but really there is quite a bit of diversity in terms of approximation by neural networks. And the second question, what can we do if we have vanishing a gradient, for example? So that's a good point indeed. Sometimes the gradient just becomes 0. So sometimes it's small for a while, or sometimes it's 0 completely. And this is a problem that is recurrent in neural networks, in particular for deep neural networks. It's not specific to meaningful games here. So if you have a vanishing gradient, I think the simplest, the most straightforward things is maybe to change the architecture, changing the activation function, adding some other connections, etc. And there are some architectures that have been designed specifically to target this issue. For example, using gates and other tricks. So yes, if you have maybe some specific problems, you can check the literature, or you can write to me later if you want. All right. So on this this method, I want to show 3 examples actually. The first one is linear quadratic. We have already discussed it. We have a benchmark solution, so it's really good because you can check if the method converges. And here, if you look at these plots and if you look at the reference, what we estimate on the left is a loss function. So this is what you are trying to minimize. But what you see so this is normal somehow that this one goes down. But what you see on the right is the L2 error on the control with the true control, because you can estimate it. I mean, you can obtain it using the ODE system, right? So you take the ODE system, you compute the optimal control, and you compare your neural network with this one, and you can really estimate the error. So here you see the error for different number of particles, different number of time steps, and the error improves when you take more neural network, more parameters or more time steps. You can see that sometimes the loss is kind of stuck. So you see a plateau for a few thousands of iterations, and then suddenly the neural networks find a much better configuration. So this is not surprising. It happens all the time. So yes, we can discuss that for many hours, but it's a phenomenon with neural networks. Another example, which is not linear quadratic, but almost, it's called mean LQG. It was introduced by Salab and et al. And Ron Malamé and co-authors. And here I use a version which is maybe a bit closer to the problem studied by Ashdu and Ladri, in which you have a room with two doors, and the crowd wants to exit the room. So this looks like the simulation I've shown this morning, except that one of the two doors is going to close randomly. So you want to exit the room, but you don't know which door is going to close, or if you want, you don't know which door is going to open. One of the two is going to open, and the other one is going to remain closed. So this is an instance of what we call common noise, because it's a noise, it's a random event that is going to affect everyone in the room. And people try to anticipate that on average. You cannot anticipate it perfectly because it's random. So here I take a slightly different version where people are going to start. So I'm going to take an initial position here. I'm going to take an initial distribution centered around this point. And then there are two targets here and here. So C1 and C2. And at the end of the game, you would like to be close to one of these two targets. You don't really care which one, but the point is one of them is going to disappear at time t/2, capital T/2. So at the beginning, you see both targets, but at time t/2, one of them disappears. So if this one disappears, of course, you would like to end up around here, right? But until time t/2, you don't know which one is going to disappear. So actually, if you try to apply the techniques I've described before, it's not completely impossible, but you are going to end up with a system of 6 PDEs. And the intuition is that you are going to have one PDE. So let me represent it like this. You have your interval for X maybe, and then you have the domain in time here. But the point is that time t/2, there is an event. This is time capital T. And so for the second part of the time, you have basically a branch, and you have different PDEs depending on what happens, right? So you have one system, forward-backward system here. And then here you have two possibilities of forward-backward system. So you end up with a system of 6 PDEs. So it's still possible because the common noise is very simple. And so we use that as a benchmark to check if the deep learning method also manages to solve this problem. We cannot solve it without a small modification. We add the realization of the noise in the neural network, but not the whole trajectory. We cannot anticipate the future. So we just put the common noise at the current time. So up to time t/2, you don't know anything. And at time t/2, then you see which target has disappeared. So you can choose your direction accordingly. Okay, so at the beginning, you see this. So here I'm plotting together the two scenarios, two realizations of the common noise, one where the common noise is going to be on the left, one where the common noise is going to be on the right. But at the beginning, the common noise is just 0. The dashed lines are the densities obtained by the PDE method. So basically the 6 PDEs that I solved by finite differences. And the histograms are the results of represents the results obtained by the method with deep learning, meaning that you compute the optimal control and then you plug it in the dynamics for n particles, and you obtain a histogram in this way. And I want to see if the densities look similar. So at time 0, it looks similar. Then you see the density concentrates. So why does it concentrate more and more? Well, the reason is that there is another component in your cost, if I go back here, which is that you want to be close to the mean, right? Part of your terminal cost is the distance between you and the mean position. So one thing that you know for sure is you want to be close to the mean. But the other thing that you don't know for sure is you want to be close to the target that will remain, right? So this one you don't know. So what you do at the beginning is you just concentrate more and more to be closer to the mean. And then when you know which target is gonna be here at terminal time, then you move towards this target. So that's exactly what we see here, concentration. And then the two scenarios are different. In one scenario, people will go to the right. In the other scenario, people will go to the left. And they don't reach exactly the target. Why? Because there is a cost to move. So moving quickly is expensive, and maybe it's too much effort. So you move towards the target, but not exactly at the target, not exactly until the target. Okay, and we see that throughout the simulation, the solution obtained by PDE, so finite differences, and the solution obtained by this deep learning method match pretty well. So for this example, you don't really need deep learning. Same thing for the linear quadratic one, you don't need deep learning. This is more for the sake of benchmarking the method, right? It's a new method, you want to know if it works, then you should use examples for which you know the solution, just to convince yourself. A last one in the same spirit, this is a model of price impact introduced by Carmona and Lacker. So what is price impact? You have a group of traders trading on a market, and when they buy or when they sell, this influences the price, right? So you want to incorporate your impact on the price and the impact of the rest of the population when you do trading. This is really a toy model, so I don't think you are going to earn billions by applying this MFG model, but it's just a kind of toy model for this phenomenon. So here, S is the price process. So the price is the evolution of the stock, right? So this is the stock which evolves, but you see that the evolution is given by a Brownian motion for simplicity, but it is also, it has a drift which is given by the mean field term. So nu here is the distribution over actions of the population. If the mean action is large, it means many people, for example, are buying. So then the price is going to go up. If the mean action is very negative, everyone is selling, so the price is going to go down. Then you have the inventory. So inventory is how much you have in the stock, how much, the quantity you have of the stock. The typical agent's wealth is how much you have in cash. So this depends on your stock and the value of the stock, but also the cash that you have. And I mean, all of that is going to be combined to give you the value of your portfolio. So the value of the portfolio is how much cash you have, and also your portfolio, I mean, your inventory multiplied by the value of the stock. Okay, so the difference with a single agent model is that you have this price impact here, which is going to be the result of the whole population, right? And here I'm considering a mean field control version, whereas the original one was mean field game. And in this mean field control version, the agents are cooperative. So you can imagine a large group of traders, maybe in a single hedge fund or bank, maybe. So the goal is to minimize this cost, where you see alpha appearing everywhere, and alpha also appears in the distribution because you control the distribution directly. So in fact, equivalently, you can get rid of the other variables you can get rid of s, you can get rid of k, and you can rewrite everything just in terms of x, so that the problem is just in dimension 1, because x is one-dimensional. We take C to be quadratic and G to be quadratic. And then the nice thing is that we have a linear quadratic. This is another instance of a linear quadratic now mean field control problem for which we have an explicit solution. So I will show a code to solve this model. On the left, what you see is for different x. So the x-axis is x, and the y-axis is the value of the control. Different colors are for different time steps. So at the beginning, you are, oh, sorry, time 0 is the red one. So it is this one. This is t is equal to 0. You see that it's linear. The line is like the ODE solution, and the dots are the solution by the deep learning and Monte Carlo method. And then as time goes by, you see that the control goes up. So this is at t equals 0.9, which is almost capital T. And more or less, the solution obtained by deep learning follows this. On the right, this is the evolution of the distribution over X. So the one that appears in the problem is the distribution over actions. The one that I plot here is the distribution over X over the inventory. And you see that at time 0, the position is quite large. So traders tend to have a large inventory. And then as time goes by, they liquidate and they have a smaller inventory. And here, because of the balance between all the terms, maybe they don't liquidate completely. This is for the choice of parameters given below, and in particular for gamma equals 0.2. So let me go back here. Gamma appears in the price impact. So gamma is this. So you can imagine that with a small gamma, it means that you have very little impact on the price. I mean, the population together has little impact on the price. If you take a large gamma, it means you have a large impact on the price. So here you see people liquidate. Now, for the sake of illustration, I try to take a large gamma. Gamma equals 1. So I don't have any specific units in mind. So gamma equals 1 doesn't mean anything, but it's larger than 0.2. And in this case, on the left, you see more or less the same kind of shape. But what you see on the right is that people start with the same inventory, same initial condition. Then as time increases, they liquidate. So it goes in this direction if you look at the colors. But at time capital T, I mean, close to time capital T, they start buying again. So they start recreating an inventory. So here there are two phases. They liquidate, and then at some point they start buying again. And this is not a mistake of the deep learning algorithm, because you see the same thing with the ODE solution. And I think what happens, maybe, I don't know I would be happy to hear your explanations. What may happen is that when gamma is large, the population has a large impact on the price. They are cooperative. So what they do is at some point they decide to buy a lot, because close to the time, because when they buy a lot, the price is going to go up, which in general is not a good thing. But at the terminal time, you are going to get a lot of cash if the price is very high. So it's in your interest to make the price go up, because when at the terminal time you are going to count how much you have in your portfolio, the value of the stock will be transferred into cash in this very simple model. So there is a sample code. Let me show you. Let's see, I have it somewhere. I have it here. Okay, so all right. So as usual, the code is just for the sake of illustration, but I hope you can use that at least to maybe learn these techniques, and you can play with it. So this notebook for this one and the one I'm going to present next, and also tomorrow, I was helped by Yuqian Zhu, who is a former student from NYU Shanghai, and he's going to do his PhD at UIUC, and he helped me to clean and put this in a nice notebook form. So here you have a notebook where there is a problem formulation recalled here. There is a class for the price impact model where basically you define the drift, the running cost, and the final cost. So you could adapt that for other problems, right? It doesn't have to be this one. You just need to implement the drift, running cost, and final cost. You don't need to derive any optimality condition, right? This method does not rely on FBSDEs, PDEs, or anything. You just take your problem, just take the dynamics, the running cost, implement that, and run stochastic gradient descent. So it's very straightforward. It's very easy to implement in some sense. So you can modify these and play to implement for a different model. Then in this class, for the what I call the direct approach, because there is no optimality condition, you basically need to define the sampling, so x0 and the increment of the Brownian motions, and the loss function. So the loss function consists in a loop in time where at each time you have to compute the mean, because here it's an interaction through the mean, and you compute the cost here by calling your problem that is defined above, the class for the problem and the running cost. Let's see. So I will just keep going down. There is a function to compute the gradient, one step of gradient, and there is this train function here. So train is basically running stochastic gradient descent for a number of iterations. And at each iteration, you do one step of gradient descent. So, okay, below is a class for the ODE solver. So here, this is to solve the ODE. I will not discuss that because it's similar to what we did the first day. And then here there is a definition of the neural network. So here we take a neural network with 3 layers and 100 neurons on each layer. A ReLU activation function, which means a positive part actually. Okay, I will come back to this comment, and then you use your solver. So the one called mysolver.train is going to do the training. So what I skipped when I described the solver is where do we see the neural network, right? So we need to discuss a little bit where do we see the neural network. So the neural network should be used as a control, right? So in principle, it is used when we make X evolve. So here you see X is equal to X plus something. So we are updating X. We have the drift, we have the sigma, and inside the drift, there is the control. Okay, so how do we get this control? Well, here you see control is obtained by applying the neural network at X and T. So we concatenate X and time, and we pass this as an input to the neural network. So, of course, there are quite a few details to discuss in the implementation. In particular, it uses a population of samples, so you have to be very careful about the dimensions. Typically, deep learning works with tensors instead of matrices, but I will skip all these questions for now. I can come back to this later if you have questions. And here I ran it while preparing the course. So for 1,000 iterations, you see that the loss decreases a little bit, but you can run it for longer. And in fact, so this is a plot of the loss, the training loss, and the testing loss. So we usually distinguish between the loss computed during the training, and this is using the samples that are used for the gradients, and the loss computed with testing samples, which are not used for the gradient descent. Here, it doesn't make a big difference because anyway, we generate samples using Monte Carlo. So training and sampling is not so different. It's not like if you have a finite data set. Here we have an infinite data set. We can sample as much as we want. But still, it's good to distinguish between training and testing. And then a few lines of plotting, and you see what we get at the end is for different time steps, t equals 0, 0, 2, 0, 4, the exact solution, the ODE solution in red is matched pretty accurately by the control learned using the deep learning method. So this is really the output of the neural network. What you see, the blue dots are really the output of the neural network for different points X. And they align pretty well. So if you plot the neural networks everywhere, you might see errors around here, for example. Maybe the neural network is not accurate here, but somehow we don't care because the mass is concentrated around 5 at time 0. So the neural network has been trained to be accurate in this region, and it's not necessarily accurate somewhere else, but it doesn't matter for our mean field control problem, right? So the question of training, where do you train the neural network is important, and I think it's good to keep it in mind. But here somehow we train naturally on the good region, on the important region, because we use Monte Carlo samples generated by the correct dynamics. So naturally, we are going to explore the important region of space to train the neural network. All right. There is one comment that I left, and you can play with this code, but maybe I will discuss that tomorrow in more detail. On the last layer, there is no activation function, and this is on purpose. So on the last layer, we want the neural network to output any real number. We don't want to constrain it, for example, to be positive or to be between 0 and 1. In some problems, it could make sense, but here the control can take any value. So the neural network should not have any constraint on the last layer. You can try to play with it. For example, put a sigmoid activation function, and you will realize that the neural network is probably not learning very well. In particular, let's see. Yes, so if you put a sigmoid activation function, it means the output of the neural network will be between 0 and 1, for example. So if it is between 0 and 1, it will never be able to output this because here the values are between -2 and -6, right? So if inadvertently you put an activation function on the last layer, maybe you will be in trouble, and you may believe that maybe the algorithm is going to converge because stochastic gradient descent is going to minimize the loss, but you are minimizing among a very bad class of function because you are minimizing over functions with output between 0 and 1, for example. So you will not see any issue in the loss function. It will decrease. You will believe that it has converged. It has converged in the class of function you have defined, right? So maybe the optimization error is not so big, the estimation error is not big. What is failing is the approximation error, which is the first type of error I described in the slides. All right, I don't know if there are any questions before I move on to the next method.
Mathieu, there is one question.
Okay, thank you. So there is one question about how to choose the structure of the neural network. Yeah, it's a very good question. So I don't have a normal answer. I don't know. I think it's really by trial and error. So here you can play with it. For example, if you reduce the number of layers, if you put just 2 layers, and if you put like 10 neurons, for example, it will not work very well. This I tried before. If you put many more, it will not work much better. So somehow you try to strike a trade-off between having a rich enough architecture so you can approximate well the function, but also not too complicated. Otherwise, you have too many parameters, and it takes a very long time to do each gradient step. There is one feature that is observed in deep learning, which is that over-parametrizing helps. So sometimes even, so here, okay, this is a good example. Actually, here, we are trying to approximate a linear function. So actually not really, because it's a function of time and x. So as a function of x, it's linear. As a function of time, maybe it's not linear, but you see that, or maybe actually it is linear as well. But in any case, it's a linear function. So in principle, you need very few parameters, right? Maybe just 3 or 4 or very few parameters. But in practice, if you take a neural network with just 4 parameters, it is not going to learn very efficiently. So there is one question, which is the approximation error, the theoretical approximation error, which is about. So let me go back to illustrate this, because actually, it's connected to the slides. So I can go here. Up. Sorry, I'm trying to connect. I don't know why it's not connecting. Okay, I think now it's okay. So let me go back to these types of errors. Where is it? It was, yes, somewhere here. So what I'm trying to say is there is the approximation error itself, which is just about this part, but this phi star, so maybe you could say for linear function f, if I know that the function is linear, for example, I would need just a few parameters. This is true from the point of view of approximation error, but from the point of view of the optimization, it's not necessarily true. And it turns out that when you over-parameterize, you use many more parameters than what you really need. It seems that the neural networks finds more easily a good configuration, which is going to minimize the total generalization error, even though in theory, maybe you would need just a small number of parameters. So the question of training is really important. Now, I don't have a good general answer for the architecture. I think it's really problem dependent, unfortunately, and it's part of, or fortunately, because it's more fun, but it's part of the work to tune the neural networks and to choose the architecture. Another question, is mu given or determined after each time step? So yeah, it's also a good question. Let me go back to here. So you have your neural network here. You plug it in order to compute xj for every j, and you make the whole vector evolve. And given this whole vector, so for the whole population, then you can compute the empirical distribution. So mu is not given a priori, and you update it at each time step based on the evolution of x, based on the evolution of the group of particles. So it's really done along the way. All right, so another question, so we can approximate any continuous function by neural networks due to density. Yes, at least on a compact set. So maybe not everywhere, but if you have a compact set and a continuous function, you can approximate it by a neural network, even with a single hidden layer. You don't need a deep networks, provided you take it wide enough. But when I say wide enough, it could be, I don't know, billions of parameters. So maybe you don't want to use a wide enough, maybe you don't want to use a wide neural network. You are going to use a deep neural networks. And there is a trade-off between depth and width. So sometimes taking a deep networks could help. But basically, yes, universal approximation says that you can approximate any continuous function on a compact set. All right, thank you. So let me move on to the next method. So we have seen this, we have seen this. Okay, so let's see. So maybe let's do it like this. What I can do is I can describe this method, and then I have another section about 2 examples of extensions, but maybe I can discuss them tomorrow before starting the following lecture. So we don't have to rush through all the slides, or if we have time, we can finish, but feel free to ask questions, even if I don't have time to finish all the slides. Okay, is there another question? Okay, another question. So how about when the control is dependent on mu? How can we approach that? Yes, it's a good, very good question. Thank you. So actually, I mentioned that a little bit later in the sorry, actually I mentioned it here. I have one more slide, so thank you for reminding me after the code. So in fact, in general, you don't need to put mu in the control because mu in the mean field, at least in the mean field regime, mu evolves in a deterministic way. So in principle, mu evolves in a deterministic way. So mu at time t+1 is given deterministically in terms of mu at time t. So if I have a neural network, which is a function of t, if I have phi theta, which takes t and xit, this dependence on time hides a dependence on mu t controlled by phi theta. Why? Because if you give me phi theta, I can solve implicitly. I can solve the Kolmogorov-Fokker-Planck PDE, and if I solve this KFP, I have mu at time t for sure. So I don't need to give this as an input to the neural network. Somehow it's just a dependence on time. Now, if you have common noise or if you have other specific aspects in your model, then you might need to take into account mu as an input to the neural network. And so this is something that we have explored in a few papers, but in particular in this one, we try to extend, so the one at the bottom, we try to extend what I just presented, exactly the same method, but plugging the distribution. And in that case, you need to do an approximation. So one possibility is to use an empirical distribution and symmetric neural networks. Another, so you can use maybe empirical distribution. You can use maybe histogram. So you discretize space and then you approximate the distribution by the values at some point. And maybe you can also use moments. So we have seen that in general, moments are not enough, but it can be a relevant approximation in some models. So in this paper, we tried these 3 approximations, add this to the neural network and see if it converges. So I hope this answers your question, but thank you for your question, because I was about to skip this slide inadvertently. But there's still a lot of work to do. So I'm not saying everything is done. There is a lot of work to be done in this direction. There are many variations. You can put 1 neural network per time step instead of 1 neural network for the whole time horizon. This type of method has been extended to finite player games by Joëmeng Hu. So she has several papers around this topic. And we also have a recent survey on this type of methods together. Extension of mean-field control, as I presented here, is based on the work with René Carmona. But simultaneously, Jean-Pierre Fouque and one of his students worked on mean-field control, even with delay. Maximilien Germain and Xavier Varin also worked on this. And Agram and collaborators also work on this type of methods. And there are probably also other papers that I'm not aware of. So now, this is good for mean-field control, but what about mean-field gaming, right? Mean-field games is not a control problem. It's a fixed point problem. So we cannot apply directly this technique. If I parameterize the control and I minimize, what do I do with the distribution? I can freeze it, but then I need to update it. So I can be back to this fixed point iteration, right? So I do fixed point, and inside I use deep learning for the control problem. This would be one strategy. Another strategy is to use MKV FBSDs. So for example, using Pontryagin maximum principle. And the question here that I want to tackle is how to solve Makhine-Vlasov FBSDs. So if we forget Makhine-Vlasov for a moment, let's start with a standard FBSD. This FBSD has a terminal condition. So there is dxt equals to something, and x0 is given, and there is dyt equals to something, and y at time capital T is equal to a function of xt, basically. Okay, but this yt has a value at time 0. It's just I don't know it, right? But if I start from terminal t, I solve the SDE, I will end up with a value at time 0. So maybe what we can try to do is to try to guess the value of y0, because if I have y0, then it becomes a forward equation. I can solve it forward in time. So this will be the intuition. We try to find y0 such that the terminal condition is matched here, and we will use that as a loss function. So in fact, this reinterpretation or rewriting of FBSDs is not new. I think it has been already in the work of Coleman and Joe. So and then by Sannikov. And more recently, it has been used in combination with deep learning in the work of Wenan He and Jieshun An and Arnold Jensen. So let me explain the idea with mathematical symbols. You have a forward-backward SDEs, and what you do is you try to guess y0, and you also need to guess z. So there is another unknown here, which is z. So I had a question this morning. Z is basically the derivative of y, if you want, in some sense, but we need to find it. Otherwise, I cannot simulate y forward in time if I don't know z, right? So I need to know z at every time. So I guess y0, I guess z at every time, and I see if I match the terminal condition. And if not, it means I have to correct my guess. So in fact, here, we end up with a problem of this type if we look for y0 as a function of x0, and if we look for, so here, and if we look for zt as a function of t and xt, just using Markovian controls. The goal is to minimize this cost. And if I have a true solution to the BSD, then I should be able to make this loss exactly equal to 0, right? So ideally, I would like to make it equal to 0. So I know exactly where the loss should go. The loss should go to 0. Okay, so this is a new optimal control problem, which is a bit special because you control. So you can, it's an optimal control problem where the state is x and y, right? So the state is larger than before. And I control part of the initial state and I control the volatility, right? So in fact, in everything I've said so far, I've avoided the controlled volatility because it's more cumbersome. But here, this is an example where you have controlled volatility. And the question is, well, okay, can we solve this optimal control problem, right? So it has been used previously from a theoretical point of view, but numerically, what we can do once we realize this is an optimal control problem, we can use the method we described before in the previous section, where we replace Z and Y0 by neural networks. So notice that this optimal control problem is new in the sense it is not the same as the original problem. So maybe you start from a stochastic control problem, you use Pontryagin principle, you get the forward-backward system, okay? And then you rewrite it in this way. This problem is not the same as the original one, okay? I mean, except maybe in very, very special cases, but in general, it's completely different, right? So we are not going back in circle. We are really defining a new problem. Now you could say, okay, if you have an original optimal control problem, why you go all this way to a new problem and then you use deep learning? Why don't you solve the original one, right? So I agree. For standard optimal control problem, I don't know, you could tackle directly the original one. But for mean-field games, it doesn't work because mean-field game is not an optimal control problem. However, it is going to be characterized by an FBSD. So from the FBSD, we can define an optimal control problem and then solve it. So this is a DBSD method of Wen and E and co-authors. And what you do in the, okay, there is an application to solve PDEs. Maybe I will skip this, but their paper is titled Solving PDEs in High Dimensions. The reason being that you have a connection between PDEs and BSDs. So it's true that in some sense, when you solve the BSD, you are solving the PDE. Here I will skip this. You can take a look if you want. I want to focus on Makin-Vlasov FBSDs, where now you have a mean field term. So there is a mean field term here, here, and potentially here. And again, maybe this comes from an MFC, but if it comes from an MFC, you can apply the previous method, but maybe it comes from a mean field game, in which case we cannot apply the direct approach, what I call the direct approach. So we do something kind of indirect. You write the FBSD. So here there is a little bit of work, okay, that you have to do by hand. You have to take your mean field game with your cost function, your drift, and write the FBSD, right? And if you mistake in the FBSD, well, it's bad for you because then the algorithm is going to compute something useless, right? So you have to write the correct FBSD. Then you apply the same method. So let me directly show the full slide. You get this, and you have an extra L here, which is a law of X here, here, and here. In fact, I should, no, okay, I think the way it's formulated is correct. So there is a law of X everywhere. So this is an optimal control problem with a forward, which is xt, I mean, one state, which is two-dimensional, which is xt and yt, or at least it's a double dimension, because you have xt, yt. They both of them evolve forward in time, because y0 starts from this condition, and you pay a price if you are far from the correct terminal condition. So here we know capital G, we know capital B, capital F, but you have to compute them, right? This capital G, capital B, capital F are completely defined by your model, running cost, terminal cost, and drift, but you have to express them. Okay, so this is an optimal control problem, but it is of mean field type because you have the law of X, right? So it is a mean field control problem. And for this one, you can use the method I described before, the direct approach, what I call direct approach. So the idea is to parameterize Y0 and Z by a neural network. Okay, so this is a summary. What is in red is a neural network. So you need Y0 and Z, Z0, and 1 until Z and T minus 1. You can put separate neural networks, one for each time step, or you can put a single neural network for Z, which is a function of time and X, if you prefer. So here, where does the randomness come from? Same as before, X0 and the increment of the Brownian motion. You don't have any running cost, you have only a terminal cost, which is your terminal penalty for not matching the terminal condition of the BSD. Okay, we have a few minutes left. So let's see how many slides I have. Okay, maybe I just go through these slides and then I leave some time for questions, or I can show the code if we have enough time. So I'm going to show two examples. One is borrowed from a work that I already mentioned of Chassagne, Delarue, and Crison, which was what I described this morning with the PCAR method. So you remember the PCAR method where you do iterations over a small time step and then some global algorithm has been used to solve this example. And so this is an example that they introduced, and it's really nice because you can study the influence of the parameter rho. So here you have an FBSDE with a parameter rho, and this FBSDE comes from a mean field game. But now we are just going to forget the mean field game and focus on the FBSDE. It depends on the mean, but through a trigonometric function. So it's a dependence on the first moment, but you still need to understand the whole distribution somehow. Okay, and you see that when rho is equal to 0, then the forward is just the Brownian motion, does not depend on the backward. And when rho is large, then the forward depends a lot on the backward variable. So intuitively, it should make the coupling stronger and the problem harder to solve. And what they have shown is that in their algorithm, when the strength of the coupling increases, the algorithm struggles because it's based on this forward-backward iteration. And this is related to the Lipschitz constant I was describing earlier in some sense. When the coupling is very strong, some of the Lipschitz constants are going to go up and the strict contraction property will fail. So here I am borrowing one illustration from their paper because I think it's really a nice benchmark for methods for FBSDEs of Makin-Vlasov type. And their methods work very well. But when rho becomes larger, the fixed point iterations fail. And here, the method I just described does not rely on forward-backward iterations. So we managed to make it work for any rho. So this is for different rho, but there is a price to pay. So when rho is larger, we need a large number of neurons. We need many iterations, many samples, etc. So there is a computational cost to pay. Okay, it's not for free. The problem is definitely harder to solve, but it does not face the same numerical issues as PCAR iterations. It's a bit different. Another example, linear quadratic model with common noise. So this is a model introduced by Carmona, Fook, and Soon. It's a toy model where you have banks interacting and interacting through the mean of the state. So I will not spend too much time on the interpretation. You can check the papers. The idea is that X represents the log reserve of a bank. And by choosing alpha, you choose how much you borrow or how much you lend, and you can increase or decrease your log reserve. And in this very simplistic model, the goal is to follow the mean, more or less, which is probably not necessarily what banks are doing in practice, except if they are risk averse, maybe you follow the mean, but even in that case, you probably try to maximize your, maybe not the reserve actually. So, but anyway, you don't necessarily try to follow the mean, but this is what happened in this model. And this model incorporates common noise. So M bar is actually the conditional mean. And so for this model, you can check that the deep learning method for FBSD. So you take your mean-field game, you write the Makin-Vlasov FBSDE, and you try to solve it using the method I have described. And in this case, it works well. You can also check the errors. And here I provide a code, a sample code for this Makin-Vlasov FBSDE. So I will not describe it now. Tomorrow morning, I will restart with this example, maybe describe it in more detail, show you the code, and then finish these slides. I just want to mention you also have extra codes on the web page of Gökçe Dayanıklı, who was a PhD student with René Carmona and is going to go to UIC. And so here I will restart with this tomorrow, I think. So do you have questions? So yes, I can see one question. How would deep FBSD approach compare to tackling AJB KFP? Yes, with PINs-like networks. So that's a very good question. Actually, I will discuss tomorrow techniques, deep learning techniques for PDEs. So today is deep learning techniques for FBSDs, and tomorrow deep learning techniques for PDEs. So maybe I will touch a little bit upon this topic. But I will not do a full-fledged comparison. So intuitively, I think the FBSD techniques are going to focus naturally on the region that matters somehow, because you explore the process is automatically controlled using the controls that you are learning. Whereas when you solve a PDE, you try to solve on the whole domain, which is maybe you don't need to learn everywhere in practice. So maybe there is a trade-off here, but yeah, maybe we can talk more about this tomorrow. Thanks for your question. And I realized that earlier. So for this code, I also had the help of Yuchen, and Yuchen is going to go to Georgia Tech for his PhD. Sorry, I mistook earlier. Any other questions? Okay. Otherwise, comments or questions, feel free to reach out before tomorrow. So tomorrow we are going to do deep learning for PDEs. We are going to finish this slide deck, then deep learning for PDEs,